You. Sit. You're sitting. Good. Explain. This has been drawing power from the entire laboratory. For 2 days. What is it?
Good morning to you too, colleague. Anyways, yes, I have been draining the power, but not for 2 days, for 3, to create my masterpiece and life's work. This is the quantum combobulator transformalizer, and it can properly transfer and combobulate the sun's electrolight waves and turn it into renewable, usable horse newtons.
Impossible.
Impossible? No, because I've done it. All in a sleek, small package.
Improbable. But how many possible horse newtons per light meter can you even kick out?
Light meter? More like light meter cubed. Allow me to calculate the exact numbers for you. Hello there. Whoa. Why are you here?
Well, these are our new students that I emailed you about.
Yes, of course. I've read the emails about our new students. Welcome
Welcome
to our lab.
to our lab.
Today we'll be giving you a brief introduction and experience in the field of electrostatics.
You will be educated.
Educated indeed. I'm A.
I'm T.
Our last names and ages are classified, but fair warning in case we accidentally say either of those pieces of information during this video, please don't tell anybody.
We'll get in big trouble.
Big trouble.
Really big trouble. Don't say anything.
Other than that, sit back, relax, and enjoy the show.
But don't relax. You need to pay attention.
Pay attention and take notes.
So, what will you be learning about? Electrostatics. Is it? That's what we're teaching. Yes it is. So, electrostatics. It's the study of electricity, electric fields, charges, and its effect on our world and everything really, because we're all in one world, as the government tells you. So, with the electrostatics, we'll begin. You already have experienced electrostatics. When you walk on a carpet like this, with socks like those, please, and then you walk to a door handle like that over there. You can't see it. There's a metal door handle. It has to be metal. So, you walk there and you feel a shock.
A shock.
A very shocking shock. Why is that? That is because you have been charged, and that metal handle is very conductive. What does that mean? He will explain conductivity. I will be explaining induction and different types of charging and polarization and such. So beginning, how does something become electrically charged? Well, to know what something is, you need to know what it's made of. An atom is made of a nucleus. In the nucleus, there are protons around the nucleus. There are electrons. They are perfectly balanced without any kind of interruption, of course, and we'll be teaching you what happens when you interrupt this balance and change it. So, let's say something rubs against something. An atom versus a different kind of atom. One is a little bit more, more containing of its electrons. It likes to keep its charges stronger than atom 2, for example. So atom 1 rubs against atom 2. Since atom 1 likes to keep its electrons, it does keep its electrons. Atom 2 gets robbed of its electrons. And what happens then? More protons than electrons equals a positively charged atom finger. Well, this is a negatively charged atom finger. And obviously you have lived in the world, so I'm assuming that you know that electrically charged things are attracted to each other if their charges are opposite. So these charges, these atoms, will be attracted to each other since they are oppositely charged. What happens if we have atom 1 rubbed against atom 3? Then we have atom 1 and atom 3 both negatively charged. Positively charged, this is negatively charged since it likes to keep its electrons. They will get repelled from each other. Rock on, students. So, when they are repelled from each other, that is because they are Yes,
Like charges.
like charged. They're charged in the same type of chargedness. So, what happens when we do this? Well, that's a good question. The problem with that is that you can't know with your eyes. You can only know with your mind. You must learn all functions of electrostatics to understand the world around you in the electrostatic sense. That is why we are introducing you to the subject. Now, for further explanation on why everything isn't always shocking you and losing and gaining charges, on to my brother. Possibly brother.
We might not be brothers. Anyway, as my maybe not brother stated, you are constantly being shocked. Why is that? Or why are you ever being shocked? Good question. You in the back. Good question. Anyways, the reason is simply conductivity. That is it. For example, a metal doorknob is very conductive. Conductive meaning that it allows electric current to easily flow through it. If you attached a wire attached to a battery to that there doorknob, that doorknob would be very painful to touch.
Yes. But remember, for a non-static, as in the electrons do not move, charge, for a flowing current to really shock you, that is just flowing from the door to the ground. For something to really constantly be able to shock you, it has to be a circuit of conductive material, at least. It has to be conductive enough to be moving.
Indeed.
What are conductive materials, you may ask?
Well,
you in the back again. Good job.
A lot of metals are very, very conductive. Copper, for example, is possibly the most common conductor that you will see in the world. For example, if you decide to be an electrician, wires are most commonly made of copper.
They will become your life.
They will become your life.
They have become our lives.
As you can see, we have a quantum mechanizer here.
Yes.
It is made completely out of plastic.
It
is
a
because
horrible,
it is
horrible conductor.
powered with an electric core the size proportional to the state of Texas. Don't ask to what it's proportional to, because I don't know the answer. Anyways, as you can see, it is made out of plastic.
Yes.
Plastic is not a good conductor. So despite all of the innumerable power levels that are within this mechanism thingy, I will not be shocked if I touch it.
Touch it. Ouch, ouch. He doesn't say, because it doesn't shock him.
It's plastic.
But if you were to open that wire, cut off the rubber is also a non-conductor, open the rubber casing around this extremely powerful coil of wires, and touch it, he would probably die, since it's carrying an extreme amount of power. But you need not worry about yourself. You have already been basically told not to touch things that look like they can kill you. There are always signs about high voltage. You will learn about that later.
Furthermore, if this mechanism were made, or encased in metal, I should say, I would be dead.
You would be dead.
I would have been shocked to death.
Yes, because electricity follows conductors. It does not go through air easily. Why? Lightning is actually electricity flowing through the air. But air is not a good conductor, as you all know, and you should know. You have textbooks. But then how does lightning even happen? That is because the water particles in a cloud rub against each other. Yes? Yes. Write that down. That means it becomes charged. One section will become charged in one sense and the other in the other. Since charges are pulled towards opposites, and the earth, our home, allegedly, is positively charged, the bottom side of a cloud becomes... Yes, you in the back. 5 points to Gryffindor.
Negatively charged. Now, this gives the lightning The humidity in the air not only gives the lightning a medium through which to move, the earth, my apologies, gives the lightning a destination. So, you have the negatively charged bottom side of the cloud, which is very
Built up
powerfully charged.
with electrons beyond your comprehension.
You have the humid air filled with water, which is a very good conductor, as I'm sure you know.
Because everyone knows, don't put a battery in water or you'll die.
And you have the positively charged earth. The positively charged earth attracts the powerful electron current from the bottom side of the cloud, and that is the phenomenon we call lightning.
Now, does lightning hurt? Yes, because all that electricity, the electrons in the bottom layer of the cloud, has built up. It's static, it cannot move. So when it becomes strong enough to create a path through the water molecules in the air, that hurts.
It hurts
lot.
A lot.
A lot.
A lot.
Because it's all condensed through one area. Yes, you always see lightning flashes in a similar zigzag shape, but it's along a single path. Yes, this is because it's going through a single path to the ground. Now, why is that? That's because negatively charged electrons, medium becomes humid enough with water to travel through, and the positively charged ground, Earth.
Lightning is a very drastic and extreme example of electrostatic processes, but it is a very good example to use because it happens all the time. We have all seen it, so it can be used to proportionally explain the electroshock that you may feel when touching something metal after rubbing up against something like a carpet.
Let's hope that was enough to entice you into not leaving the building, because that would be illegal because you have seen our faces. You live here now. But tomorrow we'll tell you about more. Until then, I'm T, this is A, our names are classified, our homes are classified, and now you are classified.
Welcome to the Classified family. I hope you've enjoyed this journey through the introduction of electrostatics.
We have, kind of.
Indeed.